Guys, and welcome back to our trigonometry series. Mr. G here, and we now getting into one of the tricky sections in trigonometry, that is general solutions. And I just want to introduce this to you by showing you where actually they come from. So I've got with me here, as usual, my graphs. I like using these graphs whenever I talk about trigonometry, and so that you can really get to understand what is going on here. Now, if you notice, check this out. Where do general solutions come from? So I'm going to draw a line here, a straight line. Okay, so I'm going to draw a straight line here, probably from there to there. Now, one thing that we must pick up from this is that for different x values, okay, there's an x value here, there is an x value here. I think last time we established in one of the videos that actually the x value there is 30 degrees, okay? So maybe if I should just show you, let's use x, let's use y, and I hope you've got your Desmos app, okay, somewhere in your phone. You can play around with this. So I showed you last time that actually we agreed, and I showed you that the value here is 30 because sine 30 is half. The value here is 150 because sine 150 also gave us a half, right? Now, here's the intriguing thing. Down here, we also have a half, okay? So I'm going to put a line of different color, okay? I'm going to put a line which has got a different color so that we can look at this, from those two perspectives. So I'm going to draw another line right down here with negative half. There it is. Okay, so there's my second line. So what I want us to notice, as I have already made you notice, is that for different x values, that we get kind of the same ratio. Now here, I'm just working on an interval of minus 720 to 720. That's my domain. And you can see the sine graph behaves in the same way, meaning it oscillates between -1 and 1. That's another important fact that we must establish, or we must know, regarding general solutions. Okay, I stated it when we were doing some identities. Okay, and when I was showing you some stuff around the triangles, I am now going to show you the importance of understanding this concept. And remember, that is the same case actually for the cosine graph. I'm going to put up the cosine graph here. You can see the cosine graph is in blue. It also oscillates between -1 and 1. And this happens infinitely, okay? Infinitely, meaning from minus infinity to positive infinity. This will just be the case, okay? Unless, of course, you fiddle around with the amplitude and all that, which we also don't do much, because even if you have 2 cos theta equals to 1, you got to divide by 2 to put that in standard form. So this is what we'll always be working with. So general solutions come from this fact, guys, that on the sine graph, okay, you are always going to, whether sine or cosine, you're gonna find yourself in a position whereby you are finding the same ratio but different, using different angles. Okay, here is just that the ratio is negative, and we will expect that because sine is negative in the third and the fourth quadrants. Okay, then what happens, it's just a repetition. You can see this pattern from 360 to 720 is just a repetition of what is happening from 0 to 360. Okay, so this happens infinitely. What am I saying? I'm saying yes. For any trigonometric equation, when you find a general solution, actually, you have a kind of given us an idea of the points or of the x values that will give us a certain angle, okay? Or not a certain angle, rather, because x values are the angles. That will give us a certain ratio. So finding a general solution, you are basically finding a set of x values, okay, which are angles in this case, which will give us one and the same ratio, okay? That is basically what general solutions are. So I've just established there are infinitely many solutions, okay? And for that, you will see, I'll explain it when I do it in writing why there are infinitely many solutions, or rather, what do we use to represent the infinitely many solutions, okay? Then the other point that I should establish also here is that we are then in dealing with general solutions. One of the critical things that will come out here and then will be the sign, the sign of the ratio, whether the ratio is positive or negative. So when the ratio is positive or negative, guys, you always need to know where, in which quadrant is that graph positive or negative. So here you can see with the cosine, the graph is positive in the first quadrant, negative in the second and the third, then positive again in the fourth. As for the rest, it is just what? It's a matter of repetition. Something interesting about the tangent is that actually the tangent, look at this, from 0 to 90, okay, look at that, the tangent is up. From 180 to 270, the same pattern. Now I want you to establish something here. In the first and the third quadrant, in other words, the tangent is behaving exactly the same way. In the second, that is between 90 and 180 and 270 and 360, the tangent is also behaving in exactly the same way. And you will see why, or rather you will see the implication of this when we do the general solutions. Okay, you will see in some cases for 10, we just kill it at 180. Why? Because already after 180, there will now start to be what? Repetitions. Okay, that is one of the things. And again, like the other functions, you can see for different x values, okay, we're gonna hit the same ratio now and then, okay? So that is where, guys, general solutions come from. So instead of having to plot the graph and find those x values, we can just put it in an equation form. Are you with me? So in general solutions, you are basically looking at the trig graphs, but not literal, not in a sense of plotting the graphs. Of course, sometimes it helps to plot the graphs, but then we are just saying, without having to go through the pain of plotting and all that, can we just find the angles using algebra? Okay, so that's basically the idea in general solution, or in general solutions. Now, the last thing that I'd like to talk about is the boundary angles. Okay, I'm going to mention this here, especially for sine and cos. They are very, very important, this stuff. Now, what are boundary angles? You notice that sine, as I already indicated, oscillates between 1 and -1. Now, boundary angles are those special angles of which sine will be on that boundary. That boundary will either be 0, will be 90, 180, or 270, or 360. And why am I saying those values? Because that's what we have on the Cartesian plane. Remember, on the positive y-axis, there's 90 at the top. On the negative y-axis, there's 270 at the bottom. On the positive x-axis, there's 360 at the right, and then there's 180 to the negative on the negative x-axis. So that's why I want to talk a little chat also a little bit about the boundary angle. So 0 will be our first boundary angle. Okay, so let me make this a little bit interesting. I'm going to put both graphs there. So what do we have? Sine 0, remember sine is the what? Is this red or orange? Yeah, somewhere there. Okay, yeah, colorblind a bit. So sine 0 is 0. So you now know that by the time you see an equation that says sine theta equals to 0 or sine x equals to 0, you are dealing with a boundary angle, okay? However, on the other hand, cos 0 is 1, okay? So you know at the boundary, okay, that is the x-axis in terms of the Cartesian plane, cos 0 is 1. So the angle 0 should give you 1 as the ratio, okay? Or if we can say the cosine of 0 gives you the ratio 1. 1 over 1 in other words, okay? And finally, the second, or not finally, here's the second boundary line, 90. In terms of the cosine, when we go to 90, we're gonna get 0. The ratio is 0 when the angle is 90, okay? On the other hand, with sine, the ratio is 1 when the angle is what? Is 90. We can go on and on with 180. You can see in the case of sine, there's a 0. In the case of cos, there's a -1, okay? 270, again, we can go on. In the case of cosine, it is 0. In the case of sine, is -1. 360, it is 0 in the case of sine, and it is +1 in the case of cos, okay, of cosine. So that's another element that I thought I should just throw in. And so to conscientize you guys, so that when I say boundary angles, you're not surprised to say, now what is he talking about? Okay, so guys, that's my little story about the general solutions, where they come from, why should we care about them? Yeah, we care about them because we don't want to plot graphs and look literally from one point to the other, where is the equation going to be true. We would rather solve everything algebraically without the pain of going through these graphs here. I hope you have enjoyed this and you at least have a clearer understanding of where general solutions come from and why we have to learn or know how to solve these general solutions. In the next video, it will be all now algebra. You may say algebra in trigonometry, or you may say trigonometric algebra, which way. However, we're going to do a lot of algebra, but of course using a trig, or within the context of trig. So I'll catch you guys later. Keep well and stay safe, guys. Cheers.